Well, okay, so the organizers have asked me to speak of my work here in the lab on semiclassical analysis. The reference is a review which is found here. Of course, the purpose is to explain how this laboratory has been a very, very fruitful place to work in. And I thank the organizers for this invitation. Semiclassical analysis has known, in fact, I've also been not only lucky to be here, but to be here in the 70s, because that was a period when the semiclassical analysis actually knew a completely golden age. And I will want to explain how this lab has played an important role in particular. It is also fair, so first let me add that my memory may betray me. It will be very personal and subjective. I may overlook people or aspects, and I apologize in advance, and I stand to be corrected. It is also fair to say that this place here has benefited from very nice synergy with a few other places in the neighborhood, in particular in Orsay and École Polytechnique, with both mathematics and physics laboratories. Okay, so no, when I arrived here, actually, my memory of that is that of the landscape is that there in quantum physics there were very isolated how can I say exceptional solvable cases, and everything else had to rely on perturbation theory. It was a complete beehive of theoretical physics was almost entirely, as I remember, around perturbation theory. Outside of perturbation theory, no salvation. So, for instance, you would expand, say, an eigenvalue. You had to find some coupling constant, expand around one of those exceptional cases. You got it was singular perturbation. Interesting perturbation expansions were divergence series, and Padet-Borel resummations were being explored all the time. That was practically always. Now, there was still one rather different or slightly different approach, which is semi-classical. The idea is that quantum mechanics is based on a positive Planck's constant, but often it can be considered to be very small. And then you may think that quantum mechanics, or some part of it, may be expressible in classical terms. In one perspective, this is just another perturbation method, because you start from classical mechanics and you use Planck's constant as the expansion parameter. And that's quite true. You had a lot of such expansions. They were, again, divergent, not summable. But on the other hand, semi-classical approaches were a little more generic, because they were not confined to isolated cases, and flexible, because there were quite a number of different presentations of semi-classical methods which were tailored to the type of system or quantity that was being studied. Okay, no. I'm sorry. Yes. So this lab was very brilliant already in semi-classical approaches. Initially, I think that semi-classical methods were, or kinds of semi-classical methods, were very much used in nuclear physics, because those are very complex systems which cannot be just treated by plain perturbative approaches. In particular, in this laboratory, at least half a dozen people made significant contributions to Hartree-Fock methods, mean field theories, generating coordinate methods, coherent state techniques, Thomas Fermi calculations, and all of this, I can't explain why, but you have to take my word, they have semi-classical flavor. You can think of them as generalized semi-classical schemes. And then in quantum mechanics and field theory also, the Service de Physique Théorique was extremely brilliant in large order perturbation theory and instanton calculus, large N limits, and also analytic studies of amplitudes and Landau singularities, and all of those also had a strong semi-classical background, often in the complex domain. So I will now speak more of the method on which I worked. I spent a lot of time in this department, which is the WKB method, which is you can think of it as the mother of all semi-classical expansions. And in fact, the very nice description of the I find a very nice description of the basic WKB method is Messia's book on quantum mechanics. That's one of the best places to start off, I feel. So just to think that my own merits should not be exaggerated, I discovered that, in fact, when I was learning physics and mathematics, I was every day walking past the house where Brillouin was born, which I didn't know at the time. So that's perhaps influenced my later, but unknowingly influenced my work. So the idea here is that initially, and in every textbook until even today, WKB is presented as an approximation to quantum mechanics. And I will particularly focus on the one-dimensional WKB method, which applies to the stationary Schrödinger equation. So I think all of you know that what the WKB ansatz is. The idea is that the solution to the eigenvalue equation has dominant behavior in Planck's constant, which is exponentiated, and then the corrections are sort of amplitude, which is smooth in h bar and can be expanded. And this is the WKB expansion, which can be computed recursively. There is a whole industry of that. Again, the problem is that it's divergent and not easily summable expansion. So the trick is in that this WKB method, which at the start looks hopelessly approximate, in fact, can be made fully exact. Of course, there is no free lunch. There is a central assumption, which is that you have to assume that the potential is analytic in the complex plane. But that's often easy. For instance, the anharmonic oscillator satisfies that. And the central idea is that in exact WKB analysis, you decipher the standard complex WKB equations, the algorithmic that solves the perturbation theory in Planck's constant, as a code for the analytical continuation of the wave function in the coordinate variable. And analytical continuation is a fully exact operation, as you know. Now, that built upon various important earlier works, which started with Loret in '57, called the ramified Cauchy problem, then pseudo-differential operators in the analytic domain, hyperfunctions and microfunctions, which started in Japan but were very much studied here by Pham and Brosia-Golnitzer. I type in blue the people who were related to this department. Then Borel transform approaches to standard perturbation series, Bender-Wu, Xing-Justin, and many other people, but Xing-Justin worked the closest on Schrödinger equation, as far as I remember. And particularly important source of inspiration was the last paper of Ballian and Bloch on the solution of quantum mechanics using complex classical paths, which very curious because in fact it was secretly doing the Borel transform of the Ballian-Bloch method used Fourier transform with respect to the inverse Planck's constant. And secretly, that's in fact Borel transformation of the semi-classical expansion, but the paper never says it. You don't find the word Borel in Ballian-Bloch's paper, but that's what it is. Dingle, there's a very original treatment of asymptotic series by Dingle in England, and Shibuya's approach also played an important role. So there is a long past history before really things started. But the exactification of WKB method was, I think, really initiated by Ballian-Parisi, who brought me into their bandwagon, and this was in turn triggered by some intriguing work of Knoll-Schäfer on the WKB theory in presence of multiple turning points. Now, I will mostly focus on for illustrations on homogeneous potentials for simplicity. So I give just a few notations. When you have a problem like this, interesting objects are the spectral functions, which are symmetric functions of the eigenvalues. Ek are the eigenvalues, and one of them is the zeta function. It's like the Riemann zeta function. You replace the integers by the discrete eigenvalues. This is a confining potential, by the way, so all the eigenvalues are purely discrete. It's interesting to include the parity-twisted variant of the zeta function, where you put a -1 to the k. Then there is the other important spectral function is the spectral determinant, which has a definition using two-pronged zeta functions, but you should think of it as the characteristic polynomial for the Hamiltonian matrix, except that it's an infinite degree polynomial, but it's almost a polynomial. And the roots correspond to the eigenvalues. And the important relation is that the logarithm of this spectral zeta function expands at zero energy. It has an explicit expansion in terms of zeta values at the integer points. And this is a perfectly convergent expansion. That's, this function d is an entire function, and the logarithm has a finite radius, so is analytic in a disk. So the initial outcomes, which I will focus as an illustration of the exact WKB method, were in fact exact functional equations for the spectral determinants, which in turn implied very concrete exact identities on the spectral zeta values. I forgot if I'm not clear, please interrupt. Okay, so the starting point was the standard WKB divergent expansion, which in the case of the spectral determinant had this outcome, that the logarithm of the spectral determinant minus a divergent. Now, let me explain. There is the important variable, thanks to something called the Simanzig scaling, is a fractional power of the energy, and it's called x. And this fractional power, which is equivalent to, it scales like inverse Planck's constant. So this is the large semi-classical parameter, and the logarithm of the spectral determinant has a divergent term, one divergent term, and then the rest is a smooth expansion at x near infinity. Okay, here of course everything depends on capital N, but this is understood. So the important step is to do the Borel transformation. That's Ballian-Bloch's method, And here, Borel transform, to do Borel transform, what you do is every time you have a large x expansion with power x to the minus alpha, the Borel transform is tau to the alpha over factorial alpha, which of course helps convergence. And the exact WKB analysis consisted of combining the Borel Balian block representation with the WKB algorithm in one dimension, and that gave this result for the Borel transform of this function A. The Borel transform of this function A is denoted AB of tau, and the important result is that first it has a discrete discontinuities. It's analytic in the complex tau plane with a discrete lattice of singularities, and the singularities are located at periodic actions, which is a Balian block prediction. And now the quite surprising result that was obtained is that, for instance, let me focus on here. The A prime denotes the same function A that is here rotated by pi over 2 and transported to this new origin. The result is that the function AB has here a discontinuity which reproduces exactly the function itself rotated and translated to this point here. And at other places it's a little more complicated. You have Borel transforms of products of A, of powers of A and A prime in a perfectly logical way. This is very curious, that a function can reproduce itself at another singularity exactly by analytical continuation. It's on the other hand, the nice thing about it is that there is then once you have this, there is a combinatorial, perfectly algebraic machine that if you want to, for instance, compute the discontinuities of this function, then this diagram allows you to draw the same diagram for all the functions you ever encounter in the analysis. So it's perfectly recursive and complete. This means that in principle this function can be described in all its sheets. I call that analytic bootstrap because that has something to, it reminded of some ideas of S-matrix people. I met Malgrange when I showed that to Malgrange in Grenoble. He said, but there's a crazy guy in Orsay who was doing the same thing. In fact, this exact structure fell into a very general framework which had just been developed by Écale in Orsay, a few kilometers from here, much more general and not at all inspired by quantum mechanics. He was working on nonlinear problems in classical dynamics, more or less. So, and he imagined the very nice name of resurgence for this phenomenon that functions are reborn at their singularities. And so nowadays one speaks of resurgence analysis. Then this exact WQB analysis got further developed in resurgent direction by Pham and co-workers and people in Japanese school again who were initially trained in hyperfunctions and microfunctions. Okay, now this same information here again, I should stress this diagram is for the quartic oscillator, n equals 4. This information, then you apply Borel resummation. Borel resummation is the inverse of this Borel transformation. It's you reconstruct the function a of x by this integration, by this Laplace transformation on this line here, where there is no singularity, and the Borel transformation converts that information which I showed you for the quartic case into a functional equation for the quartic spectral determinant. Again, in this fractional, where the relation between lambda, the energy here, and x, the inverse Planck's constant is this fractional relationship. And this is a very strange ternary symmetric functional relation, which you can think of as a generalization. If you would start from the harmonic oscillator, the spectral determinant is an inverse gamma function, and the functional equation is the reflection formula. So this is a generalization of the anharmonic generalization of the reflection formula. And later, in fact, I found a more general form which has a Wronskian origin, and this is written here for general homogeneous power. Okay, now when you enforce the compatibility of such functional relations with the expansion, which I wrote here for the log of the determinant, of course you plug in this expansion, you identify term by term, and you obtain exact identities relating the zeta values at integers. Now this is the general beginning. Just look at this one. The general form is that a certain linear combination of the zeta value for every order n, at every order n, the linear combination of Zn and Zp of n is expressed as an explicit polynomial of the lower order zeta values at integers. Particular at n equal 2, this is particularly explicit because the identity has a completely right-hand side in completely closed form. And especially so, for instance, for the harmonic oscillator, you get this identity, and for the harmonic oscillator, the eigenvalues are essentially integers, so this is just the variant of zeta of 2 equal pi square over 6. But for the cubic oscillator, you get an explicit identity only for the even sum over even eigenvalues, and for the sextic oscillator, you get an explicit identity for the parity twisted sum of eigenvalues. Now the irony is, for instance, that if you compute this same combination for the trivial harmonic oscillator, you get a completely unknown number, which is called Catalan's constant, and absolutely nothing it's like the Euler's constant. It's not even known if it's rational or not. And here you have a closed form. Thank you. Okay, so later on, that is around the end of the millennium, this Wronskian relation gave rise to, in fact, I was able to show that although this relation, which is one equation for two unknown spectral functions, which are the positive and negative parity determinants, even though it looks underdetermined, in fact, it can be solved fully and exactly, and so you can use it to compute the eigenvalues and eigenfunctions of the one-dimensional Schrödinger equation for a polynomial potential. And then, independently, Doré and Tatao discovered that this type of equation was related to the two TQ relations of integrable models in statistical mechanics, and they connected my method of solution to the beta ansatz for integrable models, and that's called the ODE-IM correspondence. And it further seems that currently the resurgent functions and even the exact WKP theory find applications in many other domains where you have divergent perturbation expansion and what is called transseries, and I have just listed here a few of them. Here these are more physics on the physics side, and on the bottom they are more on the mathematical side. And last thing, now unrelated, there is another area which is higher dimensional Schrödinger equation, where much less is known. It would be nice to be able to do this same analysis, but it's completely open for higher dimensional systems. But even though it's very far from being understood, valuable work has been carried out in this department, and here are a few names of people who contributed. There is also Cartier, I forgot, on the Selberg trace formula in collaboration. And finally, let me show, so the last item, that this is the discovery that in fact you can represent eigenvectors and not just density matrices on classical phase space using a variant of the Husimi representation. And let me show you what this gives you. You can get a picture like this, which this represents an eigenfunction of a classically chaotic system, and the stars in the sky encode the eigenfunction, but this is a result of a numerical computation, and we have no analytic understanding of the distribution of these stars in the sky, except that for chaotic systems they are distributed in a rather homogeneous way on the surface. Thank you for your attention.
Thank you very much for this nice talk. Is there any question? Jean-Alain?
André, is it true that, my memory may fail, is it true that these wonderful properties that you were explaining, resurgence, this recursion formula, also extend to, excuse me, to non-Hamiltonians,
Yes.
the so-called PT symmetry?
Yes. Yes.
So they do everything works the same?
Yes, because well, I'm not an expert on that, but there are results on that direction, absolutely, because in fact it's analysis in the complex domain, so there is no.
You don't care about
you don't need
hermeticity.
to be, well, it's more complicated, definitely. But
You
there are
mentioned
results.
you mentioned that your potentials were confining, so.
Yeah, but that's an illustration. I gave an illustration of the method on the simplest algebraic case.
Another question, a comment. In the previous slide, didn't you forget your own name in these works of Balázs, Ndendemasher, Leboeuf?
Okay, but
I think you did. You're too modest.
I also forgot that I did some work on nuclear physics with Basil Gramatikos. I should have mentioned that.
Excuse me. I want to make just a few comments. And indeed, André often forgets himself, because in all these techniques of resurgence, and which is really coming back to the front of the scene nowadays, and I think it will be one of the most important tools in both theoretical physics, mathematics. And for example, one of the main tools in this resurgence theory is called the Voros symbols. And well, I just want to pay a tribute to André. Okay.
Any more question or comment? So I have a quick question. So when you show the summation of the inverse power of the eigenvalues of the Q deform oscillator, and you have this expression in terms of ratio of gamma functions with powers, right? So yes, do you have? It looks like there is some relation between L functions and period integrals. And do you know if there is any interpretation in terms of periods or motivic
no,
relation for that? Because that looks like special values of L functions in a critical band.
Yes, but okay, this is the fascinating thing is that the left-hand side is absolutely not arithmetic. Those are completely transcendental, the eigenvalues, and yet you can get some closed forms.
Yeah, it's like as well the relation that you have between the dn that is in the previous slides. Yes, no, the one yes, the one done with dn plus looks like this generalization of the Riemann identity for periods when between the period and the pseudo period. So there must be a motif behind that and a motivic interpretation.
I hope so. I cannot just say that I hope so.
Another question.
Okay, as usual, a question from quite far away, so maybe completely ridiculous. My question is, do you have any idea how the Catalan number arise? And the reason I'm asking the question is because I've seen them popping up twice in completely unrelated physics, namely in high energy integrals. And my original assumption was, thinking was that those numbers are combinatorics, and seeing those numbers in some analytic integrations, which is quite far away from combinatorics, seemed a bit peculiar. And I saw it once myself, once from some work of Matt Schwartz at Harvard, sorry. And I'm not sure exactly if you have any hints on how they can arise in the end.
No, but I think the people to answer your question are those who sit in front of me, because there you have a very strong combinatoric accents.
There's a classical book on combinatorics in which the Catalan numbers, application or occurrences of Catalan numbers are listed, and I think it takes several pages, several dozens of.
No, but this is not Catalan numbers. This is Catalan's constant.
Excuse me.
I just made a very incidental remark on Catalan's constant.
Constant. Yeah.
It's not the numbers. It's one constant, which is the sum of this. This is Catalan's constant.
Thank you very much, André. So we'll move to the next talk.